All right, so let's take a look at some um, properties in 7.3, and we're essentially just going to work through some of the examples. So in 7.2, we looked at a table of different properties, and I'll go ahead and copy those down here. That 1, just the constant 1, transforms into 1 over f. E to the at transforms into 1 over s minus a. T to a power, where the power is an integer, 1 and greater, I guess I should say a natural number, goes into n factorial over s to the n plus 1. Sine of bt transforms into b over s squared plus b squared. Cosine goes into s over s squared plus b squared. E to the at times t to the n goes to n factorial over s minus a to the n plus 1. E to the at sine, that's not an n, sine bt goes to b over s minus a squared plus b squared. And e to the at cosine goes into s minus a over s minus a squared plus b squared. So those are the transforms that we had from 7.2. Now we want to list some properties that we have in 7.3. So one of them is tied to these last two, and that's when we do the transform of e to the at times f of t of s, that all the e to the at does to this transformation is, if we know how to transform f, so the transform of f would normally be f of s, this just slides it over. So instead of having f of s, it's f of s minus whatever that exponent is. So in the transform that we originally had, everywhere there's an s, replace it with s minus a. So let's look at this one. For sine, the transform of sine was b over s squared plus b squared. Think about this as a composition. We take this, and everywhere we have an s minus, or an s, we replace with s minus a, because this e part slides this whole transformation over a units. Same thing here. The transformation for cosine is s over s squared plus b squared. If we multiply that times e to the at, every s gets replaced with s minus a, s minus a. So that's the first new property in 7.3. So that's just a translation. The next property is that if we want to do the transformation of the derivative of a function, it's s times the transformation of the function itself with respect to s minus f of 0. So for example, if we know a function, I'll just make up, if we know the transformation of sine, then the derivative of sine is cosine. So if we were wanting to transform cosine, if we know how to transform sine, so we know the transformation of both sine and cosine, but let's suppose that we only knew the transformation of sine, and we wanted to get the transformation of cosine, which happens to be the derivative of sine, then we could use this formula. It would be s times the transformation of sine. So the transformation of sine is b over s squared plus b squared minus sine of 0, which is 0. Let me see if I said this correctly. Okay, I just want to make sure I said this correctly. So for our particular function, sine is, or b is 1. We have 1 there, 1 there. So the transformation of cosine, which is the derivative of sine, is just s over s squared plus 1. The transformation of sine is 1 over s squared plus 1. The transformation of cosine is s times that minus sine of 0. So s over s squared plus 1 minus 0, so that part goes away. So yeah, so that is true. That's correct. So what if we have a higher degree derivative? So let's say we have the transform of the nth derivative of some function that we want transformed. If we know the transform of the base function before the derivative is taken with respect to s, then that gets multiplied times s to the nth power. So whatever derivative we're taking in the previous problem, for the previous version, it was the first derivative, so it was s to the first that we multiplied that transformation by. If that's a 2, it's s squared. So then it's minus s to the 1 less power times f of 0 minus s to the 2 less power times f prime of 0 minus, that keeps on going until we get f to the n minus, say that, yeah, f of the n minus 1 of 0. So once we get down to the part where we have no s's left out front, so we do a power of s times our function, a power of s times the first derivative is 0, a power of s times the second derivative at 0. Once we get down to the point where we've subtracted so much that we don't have an exponent except 0, then we do that f of the n minus 1, plug in a 0. So the only other one I believe that we have here is if we do the transformation of t to a power times some function. How does multiplying a function that we know how to transform, how's that affected by multiplying it by t to a power? So the result is we have negative 1 to the nth power. So whatever power of t we have, we're going to raise negative 1 to that power. We're going to multiply that times the nth derivative of the transform here. So this big F is, no, that's an N, not a 2. This big F is a transformation of little f. So if we know this function and know how to transform it to get the transform of this product, we take the transform of f, and whatever this exponent is, we take that many derivatives of that original transform, and then we multiply it times negative 1 to the n power. And that's a transform to s, to the s domain. So if we summarize these properties, we have the transform of f plus g. We know that that's the transform of f plus the transform of g. The transform of a constant times a function is simply transform the function and then multiply it times the constant. If we have e to the at times some function, regardless of what that function is, then all the impact this has is it shifts us over. So we take the transform of the function f, and instead of our input being s, our input is s minus a. So it's a translation a units from s. So if we have a first derivative, what do we say that did? We take the transformation of the base function, we multiply it times s, and we subtract f of 0. If it's a second derivative, we do s squared times the transformation of the base function in terms of s. We subtract s to the 1 less power times f of 0. We subtract s to the even 1 less power than that, so that would be s to the 0. And we take a derivative of f and plug in 0. So notice the powers of s are getting smaller and smaller, so we have no s's. And here, the first one is a transform, and then from here we have our function, then our first derivative. If we add another one, then it'll be the second derivative, then the third derivative. So generically, it's what we did a moment ago. For any power, we would do s to the n times the transform of the base function. Then we would do s to the 1 less power, f of 0, s to the 1 more or 1 less than that power times the first derivative, s to the even 1 smaller times the second derivative, and we would work our way down until we had no s's, and it would turn out that it would be the n minus 1 derivative that would be our last one. So the last property that we have here is when we multiply a function times t. So what impact does that have? We transform our base function. That gives us some base function f. We take the nth derivative of that base function. So if this is a 2, we take the second derivative of the transform of that base function. We wrote it differently previously. We went ahead and wrote it big F, but this and this mean the same thing. What is the transformation of the base function? Take that many derivatives of it, and then that gets multiplied times -1 to the nth power. So those are our properties for the transforms. And back on the first page, we had a list of all the transformations that we know. So if we take these transformations in that list of properties, then we should be able to come up with a pretty good set of functions and things that we can actually transform. Okay, so now that we've gone through what we're going to be doing, let's actually do some problems. So let's suppose we have 3t squared minus e to the 2t. So let's look at how are we going to transform that. So we need to transform 3t squared. So the 3 we can put out front and transform t squared, minus we need to transform e to the 2t. So we have formulas for each of those. So 3 times, if we go back to the very beginning, t to a power transforms into the power factorial s to the 1 greater power. So this is going to be 2 factorial over s to the 1 bigger power, so s cubed. And remember what factorial means. If we have, for example, 5 factorial, that's 5 times 4 times 3 times 2 times 1. All right, so that's the first one. And then if we transform e to the 2t, I'm not going to keep going back and forth every single time. But if you have that list, then the transform of e to a power is 1 over s minus that power. So our a is 2, so s minus 2. Remember that essentially is a translation. You could think about this as 1 times that. The transformation of 1 is 1 over s. So just this part, that shifts it over 2 units. So 2 factorial, 2 times 1 is 2. So we end up with 6 over s cubed minus 1 over s minus 2. So that's our Laplace transformation of that particular function. Okay, now let's look at doing 3t to the 4th minus 2t squared plus 1. So if we transform the first one, 3 times the transform of t to the 4th, so that's 4 factorial over s to the 1 greater power, minus 2 times t squared we just did, so that's 2 factorial over s to the 1 greater power, and the transform of 1 is just 1 over s. So 4 times 3 times 2, that's 24, times 3, that's 72 over s to the 5th. 2 times 1 is 2, times 2 is 4 over s cubed plus 1 over s. So let me double check myself. 4 times 3 is 12, times 2 is 24. 24 times 3, 2 carry 1, yeah, 72. So that's the transform there. If we had a need to, we could get a common denominator and put those together, but we can just leave it that way as separate terms. So let's look at doing e to the negative 2t sine 2t plus e to the 3t t squared. So remember what happens when we multiply by e to a power. We do our transformation of our other function, and then this causes a translation, a slide over. So when we transform sine, that's our b over s squared plus b squared, so 2 squared is 4, and then this makes it slide over 2 units, and it goes s minus whatever a is. A is negative 2. Minus the negative will make that a positive, so that's going to be 2 over s plus 2 squared plus 4. When we translate this one, or when we transform this one, t squared we've done several times. That's 2 factorial over s to the 1 greater power. This translates it 3 units over, so we subtract that number from s, so 2 factorial over s minus 3 cubed. All right, let's do 1 plus t squared to the 3rd. So if we look back through our list, I'll just do it this way. If we go back, we have t to a power, we have 1, but we don't have t plus 1 to a power, t squared plus 1 to a power. We don't have anything that's more complicated than just t to a power. What we're wanting really what we have is a composition. We have something cubed, that's the transformation, and then we have another function on the inside. Well, instead of having a chain rule or something that we do here, what we're actually going to do is just multiply that out. If we square 1 plus t squared, we would get 1 plus 2 t squared plus t to the 4th. And then if we multiply that times 1 plus t squared, we would have 1 times 1, 1 times t squared, 2t squared times 1, 2t squared times t squared, t to the fourth times 1, t to the fourth times t squared. So that's going to be, let's put it in descending order, t to the sixth, 2, 3, t to the fourth, 3t squared, plus 1. So that's what we're going to transform. So to transform that, it's 6 factorial over s to the 7th power, 3 times 4 factorial over s to the 5th, 3 times 2 factorial over s to the 3rd, plus 1 over s. So we just need to multiply that out. A lot of your calculators have a factorial button. 6 factorial is 720. So we have 720 over s to the 7th. 4 factorial is, we did this one earlier, 3 times 4 factorial, and that came out to be 72 and over s to the 5th. 2 times 3 will be 6 over s cubed plus 1 over s. So unfortunately, we don't currently have a way to transform directly from here, but just do the algebra, multiply that out, and then do that transformation. All right, so now let's do sine 3t, cosine 3t. Actually, let's do sine 3t, sine 5t. So there's an identity. I believe in the book they say once we get to this point that for some of these you might need to use a trig identity in order to rewrite these. So for our transformations, we know how to transform just cosine and just sine, and we know if we multiply either one of those times an exponential, we know how that affects the transformation, but we don't have one that's for two trig functions multiplied together. And if we go down to our properties, we don't have one that is a product of functions. We don't have one that deals with, well, what happens if our functions are multiplied together and we need to transform it. So with these, we need to rewrite this. And there's a trig identity that says if we have sine of an angle times sine of another angle, that is equivalent to 1/2 cosine of the angle subtracted. Now, it doesn't matter which order we have this in. We could have put the 5 first and the 3 second, since that's a product. So if we subtract those, let's say 5t minus 3t minus cosine of the angles added, 3t plus 5t. So that's 8t. So now we just need to transform each of these. So I have the 1/2 out front, and the transform of cosine 2t is s over s squared plus b squared, so 2 squared is 4. The transform of this one is s over s squared plus 8 squared, 64. And then if we want to distribute the 1/2 through, we can. Just be careful that we don't have to multiply the 2 to both of those. We could just put a 1/2 in front of this one, a 1/2 in front of that one. So let's do another. Let's suppose that we have cosine squared t. So we don't have an identity, or we don't have a formula to do cosine t to a power. That's what this is. This means if we have a function raised to a power, what do we do with that? How do we take into account that transform? We don't have a property really that does that. We have the property if we have a derivative, how that affects our transformation, but we don't have it if we just take our function that we know the transform for and raise it to a power. So what we need to do is we need to use an identity here. And there's a power reducing identity that's where if we have sine squared or cosine squared, we can reduce that to sine or cosine to the first. And for cosine, it's this. It's 1 plus cosine of twice the angle over 2, or we could call that 1/2 times 1 plus cosine 2t. So we just need to transform this. So to transform that, the 1/2 is a coefficient. It stays out front. The transform of 1 is 1 over s. The transform of cosine 2t is s over s squared plus 2 squared. So that's our transformation there.